kinds of thought processes and decision making from some of the experts in the industry, which we're delighted to have with us. We will have presentations will be available, as noted here, and we'll do a little survey at the end and would appreciate your help in doing that upon the exit of today's session. That'll help us understand how we did and provide information that will be useful for future efforts. A quick word about the organization that's sponsoring the session today, our organization, the Diesel Technology Forum. We are a not-for-profit educational organization based in Frederick, Maryland, just outside of Washington, D.C., and our program focuses on education, outreach, research, and collaboration on all issues surrounding clean diesel technology. The members of the forum are those companies that are listed on this slide, and we thank them for their support of our work and whose funding makes all of this possible. So with that, we are delighted to have with us today one of those member companies, and that is MTU On-Site Energy. And in just a moment, you're going to be hearing from Dwight Wells, a Senior Application Engineer, and Jacqueline Gautreau, an International Account Representative. And they will have a great story to tell you in just a moment. But first, we'd like to say a few words about this topic at a very general level and share with you some thoughts about why we're talking about emergency backup power and what some of those considerations are in thinking about solutions to keep the lights and power on, and we'll be prepared to take your questions at the end. So to start things off, I would like to say that this is the nearing the end of the federal government's National Emergency Preparedness Month. September has been a month where the Federal Emergency Management Administration and Department of Homeland Security recognize the importance of advanced planning for whatever kind of events we may encounter to ensure our public health and safety and our own personal safety. And certainly providing access to electrical power is one of those considerations. So today's session is coming during the month of National Emergency Preparedness. So we thank you for joining us in that time. As is noted on this slide, and perhaps everyone has some personal experience with this, I would expect, losing grid power can be caused by many different things, and many times you don't know exactly why the power went off, but that it just did. And today our focus is not going to be on the why the power went off so much as it is what to do about it and to prevent those kind of interruptions from being disruptive and jeopardizing health and safety as well as losses of productivity. But looking back, we can see the causes of some of the larger electrical blackouts in the U.S., and this is some of the most recently available aggregated data. And they can be things as simple as equipment failure or weather-related events are quite a significant cause of electrical failures, but really a whole range of things that can cause the grid to go down momentarily or for an extended period of time. We're just coming past the 10-year anniversary of the blackout in the Northeast, and I know we have a good number of folks on the call today who may have experienced that personally. That was one of the more significant power outages in the U.S. and affected quite a large number of people, took a good while to restore, and had broad implications for the region in terms of its power generation. And the cost of that 30-hour outage was pegged at somewhere between $7 and $10 billion. And on the right-hand side of this slide, you'll note the Statue of Liberty remained lit during the entire period of the blackout. And that was because the Statue of Liberty has emergency backup diesel generators, which kept the power on. So Lady Liberty was never in the dark. The impacts of the blackout were substantial on business and the economy, as has been noted. And these are some more examples of industries that have faced shutdowns at their manufacturing plants and the losses associated with that. Retailers, particularly hard hit, and airports, of course, don't fly well without the emergency power systems in place. And in New York City alone, the comptroller there estimated that losses exceeded $1 billion for those 30 hours. So for large metropolitan areas, blackouts can be quite significant. We think of the situation of a blackout resulting in a variety of impacts that can be into simple as interruptions in the work that you're doing. The lights go out in your office and you lose a document. Or they can be quite significant, disrupting the flow of traffic, transportation, and traffic signals and networks are reliant on electrical power. And we know that food processing and grocery stores, of course, relying on refrigeration, need to have continuous electrical power to assure the health and safety of the food and the products that they're selling. And, of course, then we're all interested in being able to access our internet and our money. And these are some of the most prominent personal impacts of power outages, not being able to connect with friends and loved ones and suffering the sort of the unknowns from that. All of this adds up to a situation that does cause tangible impacts to our economy and to our businesses and personal lives. So they occur throughout the country in many different regions, and this is a little bit more detail that we happen to have available, looking at the impacts from a recent Superstorm Sandy that impacted the Northeast and what that particular major weather event entailed, involving quite a large portion of the country. And much of that is still in some level of recovery today. But at the height of these events, many businesses that were ready had diesel generators in place and were able to prevent some of the losses and or continue to provide public service. And you can see some of the news reports on this slide here. And as you'll learn today, there are many considerations in extended outages of things to think about, and we hope that you're taking some notes, and we'll have some questions for us and our expert speakers towards the end of the call today. That's a brief overview and about the implications and frequency of electrical power loss from the grid. And now we'd like to move into the program today and our expert speakers. So with that, we're going to, I think, begin with Dwight Wells, who is a Senior Applications Engineer for MTU On-Site Energy. And I'm going to hand the ball over to you, Dwight, and thank you very much for being with us this afternoon.
Well, good morning or afternoon, depending where you are participating today. Thank you for that introduction. I am Dwight Wells with MTU On-Site Energy. I'm responsible for application engineering for North and South America. Basically, my team is a bridge between the industry or the marketplace and our factory resources, whether it be from a consultative basis or general training and presentations such as today. The agenda today will be broken up into two parts. For my part, I will present items 1 through 6. You'll hear a quick overview of MTU On-Site Energy. We're going to talk about the emergency standby power technology platforms. We're going to compare those technologies and the critical parts of applying emergency standby power, areas of fuels and emissions, which are all hot topics today. And finally, we'll have some application details from lessons learned to discuss my experiences and anecdotal application thoughts and concerns that you might want to consider. MTU On-Site Energy, primarily the manufacturing point that supports North and South America, is based in Mankato, Minnesota. We're a leading producer of diesel power generator sets from 30 to 3250 kW. We also have natural gas power generator sets from 30 to 400 kW for standby and prime applications. Additionally, we have cogeneration or continuous duty gas products that are manufactured in another location as well. In support of our power generation equipment, we also include automatic transfer switches, parallel switchgear and controls, and other accessories to complement a full power generation platform. MTU On-Site Energy is a subsidiary of Togm America, part of a German-based company, Togm Group. From the platform perspective, emergency standby technologies, in order of what I would consider the most widely used technologies, I'll start with a diesel reciprocating engine. I provided some acronyms: compression ignition, RICE, reciprocating internal combustion engines. These are all terminologies that you might see in some of your codes and standards, the emissions requirements, etc. These would use engines that you would see in trucks, large industrial equipment, ships, and trains, for example. Gas reciprocating engines, or spark ignition, would utilize small vehicle engines to large industrial engines, primarily fueled by liquid propane or natural gas, for example. Further down the line is gasoline engine generators, again, spark ignited. These are typically smaller generators that would be used in home standby, small offices, etc. These would be equivalent to car engines or small truck engines. Gas turbine-based generators. These would utilize large aeroderivative turbines for large power density or combined heat and power applications. I'm sure there are other technologies that could be used in this application, such as small-scale hydro, for example, and other emerging technologies. But for the basis of this presentation, I will concentrate primarily on the internal combustion engine platforms. These are the most widely used in the emergency standby power industry. I'm speaking primarily to stationary applications. However, it would be reasonable to explore mobile generator sets. Although governed by different codes and standards, many large companies may either rent, lease, or even buy mobile generators as part of its overall disaster response strategy. In cases where the emergency system is compromised, having the ability to dispatch other equipment could make a difference in the ability to serve the mission or recovery in general. I think a few definitions might be in order. Sometimes I might use some terminology interchangeably. Emergency and standby are words that are most times used synonymously, but there are differences as to the codes that are applied, the performance expectations, etc. I will try to hit on some of the high points later in the presentation. The engineer of record, along with the client, would determine which would be required. The technologies are largely the same or identical, but the performance and certifications required do impact product selection. The approvals involved, inspections, and continued long-term maintenance and reporting requirements may be impacted by the use of this equipment. Even the requirements for emissions permitting are greatly impacted by the designation and the intended mission and use of the equipment. Emergency power, in my mind, is primarily intended to indicate where backup power is mandated by code or law, or life safety, mission critical, general public safety, critical operations such as security, military, civil defense, etc., would all be categorized emergency power. Standby power sometimes evokes the idea that it's more intended as discretionary equipment for the continued process for commerce and e-commerce, food storage, convenience, etc. Again, the determination and the use is all dictated by the application and the particular mission of that equipment. The last bullet where I mentioned ESP, from an EPA perspective, there's only one category, emergency standby power, and that's a definition contained in the ISO standard 8528. I'll speak more of that in the following slides. Emergency standby power basically is the maximum power the generator set is capable of delivering. If you were to order a 2 megawatt gen set, that's what that gen set would be capable of delivering to the particular loads. Now, in the design of that particular application, it's intended to see variable power sequences, usually in the 75 to 85% load factor, as the code would call it. This rating is also based on particular stated operating conditions, areas such as ambient environmental temperature, the temperature that the air, that the unit will see in combustion and cooling of the genset, altitude of the particular site, and other conditions that may impact the design and the performance of that equipment. Usually it's to support utility power outages or testing, and from an ISO standpoint, it's 200 hours per year. The only qualifier is that EPA's limitation for this particular rating of generators is 100 hours per year for non-emergency operation. When determining a load factor for a particular genset application, it's usually based on a 24-hour period. And the standard indicates that the unit will not exceed 70% of the full power rating, or the emergency standby rating, unless agreed by the manufacturer. In MTU's cases, all MTU engines are approved at 85% average load factor. Our product range where we use an actual MTU engine is from 230 kW to 3250 kW. Now, that's not to say that if the particular demand on that genset is the full rated power that the unit will not operate there. These are standards used to determine the time between overhaul and the general performance expectations required of the standard. Considerations in applying an emergency standby power rating is typically the utility is considered normally reliable. In North America, we generally have a normally reliable utility, but could see sustained outages of longer than a minute. Again, although the standard rating allows up to 200 hours per year or less, EPA has a very specific limit of 100 hours per year for all non-emergency related operations. That would be normal operation and maintenance testing, run times associated for some other occurrences, which I'll elaborate on in a few minutes. The peak demand of an emergency standby power rating unit is usually in the 80 to 90% of the maximum standby. We see many engineers set on a standard 70% to ensure that the load factor of all participating generator manufacturers could be met. And the average demand over a 24-hour period of variable load is typically in the 60 to 80%. And this is based on field testing and actual site data that's been gathered over the years. I'm going to talk about a little bit about those platform technologies that I mentioned in the opening slides. Compression ignition or diesel fueled units are preferred and the main technology used in emergency power generation. There's many reasons for this. The ability of a diesel generator to start very, very quickly and accept the load very quickly. The main standard in our industry is the NFPA 110 or National Fire Protection Association 110 standard, Type 10. What this means is that the genset will receive the start command, start the unit, crank, and be ready to accept that load within 10 seconds. Additionally, the robustness of a diesel generator platform allows for very good transient performance. And what that means is that when that genset has to accept that load, it can accept up to its full nameplate rating in a single step. Additionally, the diesel generator platform is relatively easy to maintain and operate. It has a long history of reliable support and operation, long history of supporting emergency conditions. A small side note is something in the industry today called Biofuel. That's the ability to fumigate with natural gas for longer run times. There's some benefit for storage of fuel, currently cheaper fuel costs, extended run times, but I must elaborate on the fact that emissions could be severely impacted by this particular application. In a legally required application, there's no real substitute for a diesel engine. Now, that's my opinion, but I think just the numbers will vet out that that's probably a true case. They are rugged and perform a diverse set of needs for quick starting to load acceptance. Challenges in dual-purpose applications of a diesel for emergency as well as demand response or load curtailment could require different emission strategies and indeed a different rating. Can't emphasize enough that emissions is a huge issue confronting diesel generators today. Further down that list, the spark ignition, primarily gaseous-fueled units, are an increasingly popular alternative to diesel engines. One of the main reasons is fuel storage benefit when natural gas is the fuel. No large diesel tanks are required. When you have large volumes of diesel on site, you have to keep that diesel in proper operating condition. You have to polish and filter on a regular basis. In today's economy, the abundance of natural gas and that cost of that fuel is a huge benefit. If you have long run times that are anticipated, utilizing natural gas could be a huge benefit for the client. And then there's some perceived general benefits from exhaust gas emissions mitigation. Application of control technology, cheaper for rich burn engines, for example, using a three-way catalyst, similar to that technology that might be used on a car. Lean burn gas engines perhaps are a little more complicated, but they are, by the very nature of the lean burn technology, very, very clean. But in those conditions where you do have to further reduce the emissions, they could require more complicated SCR or specific catalytic reducers, DPF or diesel particulate filters, and DOC, diesel oxidation catalyst. Don't mean to overburden you with a lot of terms, but basically these are more expensive and more complicated emissions mitigation technologies. Further on the gaseous spark ignition technologies, first cost is generally higher due to the need for more displacement. Natural gas just has much lower BTU content compared to a diesel from an equivalent volume of fuel, so you need more engine for equivalent kW. For example, a 2 megawatt diesel genset might be one particular size, but to get that equivalent kW, you may have to go with much more displacement to get that same 2 megawatts worth of power. With gaseous engines, depending on the technology, the time to start and accept load could be severely limited, anywhere from 30 seconds to 3 minutes, depending on the technology and the scope of a natural gas unit. Size is also a factor, but when you have what we call type 10 or 10-second loads, this particular technology might not be responsive enough to meet that need. And we are seeing in the public sector, governmental type projects, a directive to use natural gas fueled product wherever possible. And again, that's for a lot of considerations, emissions benefits, as well as the cost of fuel. I'm not going to concentrate too much on gas turbines. I think it's an important technology to discuss. These are usually where you have a large power need. The power density of a turbine is much better than multiple reciprocating diesel generator sets. Quite often when you have the need for a large amount of thermal energy, you can apply combined heat and power technologies as well. These systems are traditionally very complicated and require a fairly sophisticated installation and facility management approach. It takes a lot more employees perhaps to maintain and manage this type of technology. Additionally, the time to start and accept load would not fit a traditional emergency application. The ability to ramp up to speed, to stabilize, and to be ready to accept that emergency load takes quite a lot of time with this technology. There have been in the past, I've worked on projects where diesel fuel turbines were utilized. However, the amount of fuel it would take to get benefit out of that power density would be almost impossible to accommodate. Gas turbines are a vetted technology that are used throughout the U.S. Common applications would be things such as driving gas and oil pipeline transmission equipment, as well as electric power for both standby and continuous needs. Cogeneration electricity and process steam for industrial use is probably its most benefit to large industrial users, but again, an emergency standby might be a technology that wouldn't be appropriate. Often we see in conjunction with diesel emergency gensets to suit that need, where the diesel generators can pick up your short time emergency needs, allowing time for the gas turbines to get up to speed and temperature, et cetera. The other area of stored emergency power supply needs, again, I probably gloss over very, very quickly. These are technologies such as UPS. A UPS or uninterruptible power supply is quite common. They do require some kind of stored energy, typically batteries, a rotary power supply. These are limited. These have limited time capabilities, usually in the 15 seconds in the case of flywheel technologies, up to 15 minutes in the case of batteries. I have seen larger run times. Obviously, that means much more batteries. These are complicated installations and have complicated service demands. Quite often, an UPS is used in conjunction with a diesel generator. Those are conditions where the outage of critical equipment cannot be tolerated, so you need immediate power supply, but you also need extended run times, thus the application of a diesel generator set. There's some other technologies, solar and wind-based. Obviously, these have limitations, day-night for solar, wind needs to blow for wind. But these technologies would also need some kind of storage capability, batteries, for example, to be a reasonable emergency standby power supply. These have limited use in emergency applications due to reliability, as on-demand need can be compromised. There are some hybrid solar systems that I've been involved with where in the daytime they take advantage of the solar arrays through an inverter, and and nighttime they would use a reciprocating DC generator through that same inverter to supply the load. Again, cost versus power density is still a huge issue, probably not viable for the traditional emergency standby power need. One area, and as you probably have seen in some of the news coverage of some of the weather-related catastrophe, is that of fuel. I'm going to spend a little bit of time talking about the different fuels, pros and cons, et cetera. I think this is an area in the design and selection determinations that need to be considered in great detail. Diesel has an advantage and then has the highest BTU content for the volume. That's where that displacement comment earlier comes into play. Diesel gets basically more horsepower for a particular equivalent displacement than other technologies. Again, it's combustible, but not volatile. It's safer than flammable liquids. It has some benefits for the storage and application of this fuel. And it's readily available. It's been around for some time, although the requirements are ever increasing in terms of the impact to the fuel consistency itself. Now, there's very specific regulations to the supply of diesel. For example, low sulfur requirements are in place pretty much for all of the United States. They've been in place in places like California for quite some time. But it's a major influence of exhaust emissions performance and a major impact to generator performance in general. The storage and shelf life of diesel is problematic. Certain codes in seismically active areas, for example, may require as much as 96 hours of fuel storage on site for those generators with a special seismic performance certification. May require additives, polishing, and extreme climates, heating and cooling. Spill containment and hazardous material handling needs. There's limitations on quantity in closed areas. So the need for local, what we call a day tank supply near the genset, for example, and additional main storage somewhere underground or above ground as may be necessary to meet the mission of the particular genset. Considerations for diesel fuel availability after an event, whether it's a man or nature-made event, you need to have contingency plans for the continued supply of fuel. As you can imagine from the past events, there was quite a competition to receive fuel. There was also an availability issue. I think if you noticed in the preamble presentation, there was some press releases about EPA removing requirements for ultra-low sulfur diesel because it was in such short supply. So that should be a major consideration in design of your installation, but also your general logistics. Do you have a supplier that has the ability to deliver fuel when under duress after an event? Special considerations for the design of fuel storage. You know, one of the major lessons learned we'll talk about was where the fuel was stored. Don't want to put it in basements, for example, in a floodplain. Delivery of that fuel. The fuel existed, however, the power to the pumps to deliver that fuel had lost power due to the design of the distribution of the power. And then again, there's the conditioning of that fuel, filtration, water removal, as well as a general ongoing polishing for long-term storage conditions. And then again, finally, the ease of access for replenishing fuel supplies. It's very difficult if the trucker comes to deliver the fuel and he can't get that fuel to the storage areas easily enough. Again, continuing on fuels, natural gas, it's an abundant supply and currently very inexpensive. There's some benefits to the exhaust emissions from utilizing natural gas. Fuel storage is not of a huge concern, although delivery of fuel might be a concern. Some concerns during natural disasters affecting that fuel supply: earthquakes with automatic shutoffs, severe storms or fires. In the case of some of these storms, natural gas was available fuel for gensets, but had to be turned off to allow firefighters to fight fires that may have resulted from a broken valve, et cetera. Power density is much less than diesel, requiring larger engine supply, similar output. I think I discussed that earlier, but you need a much larger engine to get the same equivalent kW when using natural gas. There are some applications quite popular. We see what's called dual fuel, where natural gas and propane would be available to power that genset. It allows benefits of natural gas with on-site storage of propane. Usually when the propane is called upon to fuel that engine, say in the case where natural gas is unavailable for one reason or another, there's usually a D rate for propane use. So when this particular technology is applied, you have to ensure that your essential loads, your emergency loads, can be supplied by that now derated engine output. And again, there's some consideration for the design. You have to have correct tank installation and design details for the delivery of that particular fuel. Converting the liquid propane into a gaseous product takes a little special design and handling. There is a fuel called biofuel. It's not widely accepted yet, but we've been seeing many inquiries from users, engineers alike. Many folks suggested that perhaps I not explore this area, but I think it's an interesting area to consider, to investigate. It's not without its risks and difficulties as well. The main benefit of diesel to a diesel application, again, let me clarify the biofuel. I think I spoke earlier in the presentation. Biofuel is the process where a standard diesel engine would actually have natural gas introduced after the filtered combustion air. So basically it's a standard diesel, but you're supplementing it with this natural gas fuel. One of the benefits is you can start and accept load on diesel. So you have the quick start, the large load block acceptance. Once you've stabilized your supply of power, then you can introduce natural gas. There's also a seamless transition of natural gas if the natural gas supply is removed. So if you're operating on diesel natural gas, something from the event caused the natural gas supply to be inadequate or removed altogether, the diesel portion of that engine will continue to operate seamlessly. If you do have natural gas, you do realize extended run times of approximately 3x of your on-site fuel storage. And that's just a function of reducing the consumption of diesel to the natural gas side of the fuel supply. Again, when you're on this particular biofuel fuel condition, you will realize a D rate of 15 to 20% from the nominal diesel rating. So again, you need to make sure that your critical loads have enough power to be supported, or that you have mitigating controls to reduce the load to that level. If you recall in my definition of emergency standby power, we have these load factors of 70 to 85%. In those cases, you'll probably be at that load factor application anyways, so probably would not need to have any mitigation to the load in reality. This next bullet about EPA is a very critical area. In the past, it was kind of an out-of-sight, out-of-mind technology. No one really asked the question, so there was really no impact from an emission standpoint. But EPA has recently weighed in on this particular technology. In their mind, there's no tampering or legal violation as long as site stack testing has been required to ensure that the original tier pollutant levels have been met. There's some benefit to PM, slight benefit to CO, but not the case of NOx, and they actually increase. So EPA is basically stating that if you do apply this technology, your normal tier rating is no longer in effect, but will allow it to be verified and reestablished by stack testing. This would usually indicate that you would have to continue that stack testing in some time period, usually 2 to 3 years. If installed, EPA considers that the original manufacturer tier certification is valid until proper stack testing is done and verified, but you also need to keep in mind the local and state regulations may have other conditions, they have other criteria that you must meet as well. I thought I'd throw this one in because I hear this term used in confusing ways quite often. Biofuel, not to be confused with the previous discussion on biofuel. Biofuel is a non-petroleum-based fuel oil, typically vegetable oils and animal fats. You'll hear when this particular application is requested a term of B5 or B20, which basically means a 5% solution of biofuel to standard diesel fuel or 20% solution to the normal diesel fuel. Some states have mandates. For example, in Minnesota, where our factory is, they have a B5 blend requirement. This is primarily intended for fleet operations or vehicles, but has had an impact on the fuel supply in general. So quite often, our units have run on B5 fuel in our test day. Obviously, the public benefit to using biofuels is that it's usually taking some fuel that would normally be a refuse fuel or thrown away at the landfills, et cetera, and get some utilization out of this. There is some reduction of the PM or the particulate matter, the carbon dioxide, and other hydrocarbons for exhaust emissions. On the negative side, there's considerable maintenance requirement. These biofuels, obviously, since they're vegetable oils and animal fats, have a tendency to separate, thus creating conditions where filters may be clogged, et cetera. So it does impact the maintenance much more severely than other fuel types. Primarily the storage environment and the shelf life is very limited. The temperature that these paraffins might drop out of solution and the fact that this fuel oils may rot, to use a term. So in my opinion, it's not a good fuel for the emergency standby generators. MTU OE will soon have a white paper to discuss biofuel content in diesel engines. Sometimes it can't be avoided due to the availability of fuels. There are mandates, as I mentioned. So MTU is trying to provide guidance on how to use these systems and how to take precautions to ensure that this fuel doesn't impact the reliability of this unit to supply its intended mission. The second, probably the largest topic in today's world are emissions, especially emissions on diesel power generator sets. Although the EPA has realized that applying stricter emissions requirements on emergency power might be problematic, they have provided some very specific scope of supply on how a diesel engine will be used and for what functions it will be used. So they allow for certain exemptions for emergency standby power applications. Current level emissions allowed, for example, Tier 2 for greater than 560 kWs. Typically, there would be no after treatment. The EPA limits to runtime of 100 hours per year for non-emergency use. Again, they realized that some of their requirements previously were restrictive and probably weren't in the best public benefit, so they've augmented their rules recently. A few of those are as follows. They allow 15 hours of non-revenue related demand response. If your genset could benefit the grid, they're going to allow part of that 100 hours to be used for that purpose. If the grid is in an energy emergency alert level 2 or worse, they also will allow that genset up to its 100 hours of operation to support that grid. So potential voltage sags, claps, or line overloads that could result in regional power disruptions, they've realized that the use of this generator is probably a reasonable application to prevent that from occurring. And then again, a term I used to call storm anticipation. Many years ago, they referred to as storm avoidance from hurricanes, ice storms, or other nature-made occurrences. In the past, you weren't allowed to run your generators for the idea that you may have an outage caused by these situations. So to avoid unplanned outages, to help support the grid for those situations, you are allowed to run your unit up to that 100 hours of runtime per year. Now, in the past, many generators were procured as emergency standby power, but through local utility programs were allowed to be used for other sequences of operation, primarily demand response, where there could be some incentives offered from the utility. Now, in today's world, the revenue-generating demand response will result in the need for a prime power-rated unit, and thus a Tier 4I certified for larger units. So you can't use your existing genset to take advantage of some revenue-generating program that might be available from your local utility. So those would be non-emergency related run times. If you have a genset that might need to base load to reduce the demand on the grid, or a CHP application where you're taking advantage of the thermal energy of a genset, that will require that you meet the most strictest emissions regulations. But keep in mind, EPA is the minimum criteria. That's the criteria that's imposed on all manufacturers to be allowed to provide technologies in the United States. However, local, state, and other criteria may dictate some other scope of supply, including after treatment. In my region where I happen to live in California, a diesel particulate filter is quite common to meet the regulations imposed even for emergency standby power. One area that I think can be explained in many webinars. In fact, at MTO On-Site Energy, we have a lot of customer events where we expound on this particular area in great detail. I think if you're interested in receiving additional information about this, please contact the local MTU distributor, one of the regional sales managers. If you have access to my email to me personally, we have a lot of lunch and learn and other materials that might be beneficial in discussing design considerations for these events, such as man-made or nature-made loss of power. The first item, wind ratings. I think wind ratings and other local code requirements for weatherproof enclosures, for example, need to be defined and built for the purpose. If they need to withstand a hurricane-force winds, then perhaps a hardened building might be a better solution, or you need to ensure that the design of that building is appropriate for the region. There are many maps from the U.S. Geological Survey and other agencies that define the worst-case conditions. States such as Florida have defined special codes and standards that would dictate the design of outdoor enclosures, for example. But at minimum, an enclosure that is designed for ASCE 7-05 would be the minimum, in my opinion. Out west, we have a lot of seismic areas, but I think as we've learned in the DC area with the earthquake from a couple of years ago, that there are many more seismic areas that have significant impact to the supply of emergency standby power. IBC/OSHPOD, as I refer to OSHPOD, as a healthcare agency in California, but primarily the International Building Code has provided guidance and testing criteria, design and testing criteria, to ensure that a particular genset would withstand the seismic event and be available to serve its intended mission. If in this industry, there's something called equipment importance factor of 1.5. If ever you see that established in your particular application, you definitely want to specify seismically certified power generation equipment. And all manufacturers in this industry have product that meets this requirement. Fuel storage, as was seen in Sandy and other natural disasters, I remember the news feed of the National Guard having to carry buckets of fuel to a rooftop to allow power for the proper evacuation of some patients. This was due to the fact that the fuel supply was located below the floodplain in the basement, primarily as a design convenience and no other consideration. Once that basement flooded, that fuel supply no longer was available to that genset. The engine generator was high and dry on the roof, but with no access to its fuel, it could not supply its reported mission. Although I'm quick to point out that there was a contrast from Katrina, perhaps, to Sandy, where arguments for natural gas over diesel could be made. But in any instance, I think it's important to analyze and evaluate the conditions and plan for those particular conditions. If you're in a particular weather-related area or near a river, or you could have a large water main running through your basement, I think considerations for the design of the supply and condition of that fuel system is very critical. We've had a lot of people talk about, designs of their facilities were proper to meet the codes and standards for a 100-year floodplain, for example. As we all know, those situations are forever moving targets for a lot of reasons. And if your mission of that emergency standby power generator is critical, then you must assume worst case and take all situations into account. I know that's hard, but if you want the benefit of MQ on-site energy, we'll be happy to provide more information on that subject. Fuel quality, such as the storage of that fuel, is equally important. Decisions on whether to have biofuels, what kind of filtration, water removal, situations such as cooling the return fuel. We've seen areas where gensets were subjected to extended run times. They didn't apply fuel cooling on that return fuel. They heated up their fuel supply and rendered the genset either unavailable, or in some cases, like with an MQ engine, that genset has to derate to compensate for that fuel temperature. So again, that's an area of design that's quite often forgotten about. Redundancy. This is a term I see in specifications and is used, unfortunately, it's used quite often without a lot of clarification. Redundancy from a genset's power supply need, you'll hear terms such as N+1, N being the amount of generators you need to serve your cited purpose, plus one additional to allow for generators that might be out for maintenance or generators that might fail from unforeseen situations. Or in cases of critical data centers, you might see an N+N where they want 100% redundancy of the power supply. That's one aspect of redundancy, but what people forget to look into is the redundancy of that power delivery, or the ancillary devices such as supply of fuel to the genset. So redundancy has to look at the entire mission of the facility. We had an N+1 facility where the power was ready and available. However, the one transfer switch that was designed to deliver that power was underwater, so the power was unable to be delivered to the loads. So temporary cables had to be rushed to allow that generator to supply that particular load. So again, redundancy is an area that requires a lot of consideration, not just from the emergency standby power generator. So that sixth item where we talk about specifying the correct codes and standards. Quite often I see a lot of specifications. I see boilerplate where documents specify either all or none of those actually required for the intended mission of the equipment. Consideration for codes and standards and certifications associated with those codes and standards are intended to ensure or facilitate a specific quality and expectation performance. Sorry about the mouthful of that particular comment, but my point is that, you know, we as manufacturers have encountered a lot of those particular situations. The paralleling switchgear folks, the transfer switch folks, all have experiences. And if you've taken all the care in providing that redundancy at the generator level and none at the delivery of that power, you could render your system unavailable for that during that event. And again, emissions, we've recently seen lots of reports and have had lots of consultants involved in the emission, as I call it, the hot button topic. Although the federal government has made adjustments to allow greater flexibility of emergency generators without the need for higher certification levels, local jurisdictions have other requirements that may require application of after treatment or other emission reduction measures, such as limited runtime for maintenance and testing. Application of certified equipment is obviously an option, but may not be the best solution. Compliant technologies may offer greater performance expectations over certified criteria, primarily due to limitations on the certification process. There's a condition called inducement, whereas you might have an otherwise ready-to-operate genset, but because of the failure of a critical component in the after-treatment, that generator is required to stop operating. So not all emissions mitigation systems are created equal. So I really emphasize that if you're embarking on a generator application, especially those applications that require large profiles, large footprint of generators, that you employ the services of an expert in that field. We have experiences from a manufacturing perspective, from the application of technologies, but each individual local state area, the conditions of your other processes on site. You may be a food processing facility where the nature of your process emits hydrocarbons or particulate matter. These would all be additive to those emissions capabilities of your power generation equipment. So again, there's a lot of consideration that on the surface of a generator supplier might seem mundane, but there could be more far-reaching impacts on emissions level. Thank you for your time today. I would now like to introduce Jacqueline Goutreau, who will provide a brief presentation on MTU on-site energy products, platforms, a couple of case studies, and how to find more information from MTU on-site energy. Thank you and have a pleasant day.
Hi everyone, thank you for joining us today and taking your time to listen to what we have to say about emergency backup power. My name is Jacqueline Goutreau. I work in the international export sales at MTU on-site energy. I deal mostly with Latin and South America, but rest of world products as well. As Dwight discussed, we have a wide variety of products ranging from 30 to 3250 kW units for emergency, standby, and continuous diesel systems. We have 30 kW to 400 kW for gas systems in Mankato. And then we also have the M2 transfer switches. When designing sites, all conditions need to be considered. Main conditions other than buildings need to include ambient conditions, altitude, dust such as in desert areas, corrosive air, and natural disasters. As Dwight was saying, natural disasters could, for instance, include the International Building Code, or IBC, which has certifications available throughout the world. In the U.S., California is directly influenced by the certification or standard. I would like to take a few minutes to go through a couple of case studies that MTU has available. First off is the Vantage data center, which is located in Santa Clara, California. This project highlights 6 3,000 kW standby generators with the importance factor of 1.5. Dwight discussed IBC conditions and the importance of having the certification available, which can be make or break. This data center provides reliable backup energy and significantly reduces IT infrastructure cooling costs and carbon emissions so that the customers can reduce their total cost of operation. This data center prefers to have a PUE, or a power usage effectiveness, of 1.0, meaning that the IT equipment uses the same amount of power as the facility. This is calculated by total facility power consumption divided by the total IT equipment power consumption. This project includes the 6 Series 4000 models with a diesel particulate filter, as Dwight was discussing, a weatherproof enclosure rated at 73 dBA, dual batteries, and dual starting motors for increased reliability. MTU was selected for this project due to the excellent load acceptance and transient performance. These units can take a full load and recover quickly within steady voltage and frequency. Right now, the site has 6 units with plans to expand to 10 units in the near future. Moving on, Marsh Creek, which is located in Alaska, is an extraordinary example of specific site conditions. This site is in a remote location in Alaska, which provides continuous power to all nearby towns. There's a wide variety of units at the site that, since installed, have been reduced fuel consumption by 30%. This has made a dramatic effect on the site by the cost sharings alone. On top of that, Marsh Creek is the only firm in Alaska that has the load bank capacity available of 18 megawatts of medium voltage needed for testing and diagnostics mandated by the code and industry requirements. Not only does this power plant provide reliable energy to the neighboring communities, but the 2 800 kW units are dedicated to the Alaskan pipeline to send crude oil 800 miles to the main oil field. For more information on a specific site condition and design considerations, I'll be able to forward you to our project center where you can see more. The Royal Jubilee Hospital is located in Vancouver Island in Victoria, British Columbia. This hospital is responsible for 500 hospital beds and is reliant on the backup generators. If anything happens to utility power, the two 3,000 kW generators are available to pick up full load within 10 seconds, utilizing a closed transition transfer switch system, so the power is never off. This power's reliability is essential for hospital applications. This project also utilizes the IBC certification and is deemed Pacific Green by the Pacific Green Energy Initiatives by minimizing the impacts on natural resources. And lastly, I'd like to talk about the Water Treatment Center plant in Washington County, Oklahoma. This is a great example of design considerations since the site was chose over 3 500 kW units instead of one 1,500 kW unit in order to expand reliability and resources for all parts of the plants, including the facility, labs, pumps, filter controls, offices, and security systems. In the past, this facility utilized one 600 kW unit, and as the plant grew, so did the demand for additional backup power. The site is located in an area called Tornado Alley and distributes water to 6 surrounding water towers through miles of distribution lines. Without this ability to supply the water to residents in the event of an extended power outage, most utility can't withstand ice storms, lightning strikes, or other severe weather. So the backup power energy is required in order to keep the power going. For more information about technical articles, case studies, software downloads, or any information on finding a dealer or an RSM in the region, there is a project center site available on m2onsiteenergy.com. This site is open to the public and available. Thank you all for your attention.
Great. Thank you very much, Jacqueline and Dwight, for that very interesting and informative presentation. I see we do have a couple of questions that have come in, and I just want to remind everyone that you can enter questions during the lower right-hand side of your screen there. And let me address the first question to you, Dwight, and it's from Phil Wright. And the question is, will a diesel engine maintain its EPA and/or CARB certifications if the unit is, quote, fumigated, unquote, with natural gas?
According to the EPA ruling, and it's not been accepted as law or otherwise, but it's a ruling based on industry and manufacturers submitting it to EPA. Basically, their indication is it will not be a violation or a tampering case, but they will consider that the original tier rating is void until stack testing is done to verify that. Now, that's not to say that a manufacturer can apply his own technology. There are a few that are investigating that now, but other than some small gen sets, I'm not aware of any commercially available at this time. So I'd have to say yes, I would be concerned that the ratings are invalid if that technology is applied.
Okay, thank you very much. Another question, somewhat along the same lines. How does biofuel application affect Tier 4 emissions certification, where an EPA has mandated the engine manufacturer be responsible for installed emissions performance?
Well, as I mentioned, there is some benefits to it in the emissions. I think PM will be reduced, obviously. However, in some cases, NOx will increase, probably in most cases. So again, it's the same. Your rating is invalid until you can prove through stack testing that the original constituent limits defined by the tier rating of EPA have been met. From a technology standpoint, we believe that's quite possible, but there is that step of having to provide that site stack testing to make that verification.
Okay, thank you. There was, I guess, a clarifying question for you again, Dwight, questioning what ruling you were referring to regarding the fumigation comment.
There was a letter issued by the EPA. They have a public forum. I guess I get copied on them through my relationship with these association groups. It was through public record and request. A question was posed, and EPA responded. I think I probably have access to that. If that could be put on the record, I can try to track that down and give it to the particular person interested in that.
Okay. Thank you. One of the questions just came in is, can you talk in more depth about the role that backup generators should play for emergency preparedness and what role lawmakers can play to facilitate that?
It's a pretty broad question, but I'll try to approach it this way. Every facility has a mission, a hospital to take care of patients. Now, it doesn't necessarily mean that hospital is going to be the place where someone might deliver patients to during an event such as an earthquake. Part of the mission might be to make the facility safe to be able to evacuate for egress and access to a facility. So the codes and standards are pretty clear on when backup power is required, the type of backup power. But in the case of the e-commerce, the IT, there aren't necessarily laws that dictate that other than the normal public safety aspect, which could be a very small portion of the total load. But the benefit to the facility's mission of providing Facebook users access or e-commerce through Amazon or other sites, the determination to have available power will dictate the role of emergency standby power beyond what I'll call the life safety or the personnel needs. So that will become the mission requirement or definition of the client and his consultants. As far as regulatory agencies, I think the system has worked quite well, like Diesel Technology Forum, other associations like EMA. They lobby government. The EPA had very strict requirements for the use of emergency standby rated equipment, which has the reduced emissions requirements. If they're not lobbied by these groups, they probably would have never realized that the overall public benefit was not being served. When they realized that because of ultra low sulfur fuels, the fact that the overall benefit to the public good when we helped avoid a regional grid failure outweighed the short-term perhaps rise in emissions, that would have never been possible without the regulatory method. That is lobbying by these agency groups, these forums and associations. So it's incumbent upon manufacturers, users alike to continue to press those needs so that the regulatory people get it right. As we've all probably encountered, there's a lot of the regulatory requirements that perhaps aren't in the public best benefit and are detract from the overall mission of providing backup power.
And let me, if I might add just a few words to that. One of the things that can be done by policymakers is examples we've learned from Hurricane Superstorm Sandy and the lack of preparedness from service stations for being able to pump fuel. And as a result of that, we've seen legislation introduced and passed in New York and I believe a few other states there that provides incentives for certain fuel depots to put in a transfer switch or invest in putting a diesel generator, or excuse me, a generator of some kind in place to assure their continuous operations. And for example, in Maryland, our home state here, the Maryland Energy Administration just recently launched the Service Station Resiliency Grant Program called Fuel Up Maryland, and it's a $1.7 million program that provides funding for service stations to pre-wire for backup power generation. And it gives them a grant up to $15,000 for portable backup power generators and the installation or fixed backup generation and or batteries. So there's some choices there. But in this case, it provides a conduit so that if there is a situation again, that a mobile generator in this case could be turned on, or one could be provisioned to that location and quickly fired up and put the power back in place and begin pumping fuel. So emergency responder vehicles and private citizens can use the transportation network. So I think that's one of the more recent and more relevant policymaker initiatives to help facilitate greater use and preparation by providing these kinds of grants and incentives to businesses to have backup power systems or readiness to accept backup power systems. Because it's, as I think Dwight has pointed out, it's just not as easy as just deciding one day you want to have emergency backup power and the next day everything works well. There's a lot of considerations and requirements there. So pre-planning is important, and obviously in this case government incentives are going to help a number of businesses that might not otherwise have made those investments be ready the next time. So not only can they stay in business, but they can keep help the recovery and cleanup efforts get going faster. Are there any other questions from our attendees today? There was an opportunity to submit those in the lower right-hand corner. You've been
Alan, there was one question.
Yes.
I'm reading here about it's kind of related to the emissions issue. Did I hear correctly that the existing gensets could not be used in non-emergency applications without meeting Tier 4? Yeah, I didn't intend to indicate that for existing gensets. There are other regulations for existing inventory, but that's a different ruling. There's some Rice-NESHAP rulings. It depends on the install date, the age of the equipment, et cetera. Quite often, depending on those situations, there is some mitigation that has to be done, but definitely you don't have to pull it out and put in a Tier 4 generator for that application. So I would refer to your existing permit criteria, and I would refer to the new rulings for Rice-NESHAP in regards to installed gensets.
Okay, and there's one additional question here. We believe that NFPA 110 requires on-site fuel for life safety systems because the utility companies cannot guarantee that the fuel source will not fail during disasters. Do you know if this rule is being applied throughout the U.S.?
I believe that is the default for what I will consider legally required installations. That on-site storage is the norm. That's primarily because a major portion of that standard is there's a certain requirement for hours of operation. 8 hours, 12 hours, 24, 72, all the way up to 96 hours in the case of seismically active equipment. So yeah, I would agree that that is the norm for what I'd call legally required life safety systems. And primarily the other systems would be for standby power systems that perhaps were not legally required. And I appreciate the clarification question. And
I think we're getting close to our ending point, but there is one question here on emissions coming from the Maryland Department of the Environment. And the question is, how could I get information on cost to retrofit an existing Tier 2 engine?
I would suggest that you would consult the local distributor of that equipment. There are many other independent third-party firms out there. I would do a Google search on aftermarket after-treatment equipment or something of that nature. But I would start with the distributor of that particular equipment. As we say in this industry, is most of the entities, primarily the distributors, are really emissions companies rather than generator companies, because that becomes a single limiting factor in the successful application of power generation these days, especially new equipment. So I would start there, but there are a lot of third parties out there that have the capability and access to after-treatment equipment to meet the rules. They also, I would suggest that you quiz and inquire about their ability to do the actual stack testing. Testing requirements for a manufacturer to meet the EPA regulations is much different than the testing that might be required on site. Different math. Local air boards may have a say in what testing they want, how often, and the type of record keeping. So But again, I would start with a distributor of that original equipment.
Okay, thank you very much. We are, I believe, at the end of our program for today, and let me turn it back to Kristen Gifford for some final important comments about what happens next.
Thank you, Alan. We did record this webinar, so early next week the recorded webinar as well as the slides will be posted on the Diesel Technology Forum website, and you will be receiving an email with this information as well. I'm going to put up a participation survey here, if you'd be so kind as to take a couple minutes to fill it out to tell us your thoughts on the webinar, and thank you very much for your participation.
Thanks, everyone, again, to our speakers, Jacqueline Gautreaux and Dwight Wells from MTU On-Site Energy. We appreciate your participation, and that for all of you who stayed with us this afternoon. And thank you very much in advance for helping us fill out the survey. We do look at that and take that information into consideration. So with that, have a great afternoon and a wonderful weekend, everyone, and we'll look forward to talking with you soon.